It is my pleasure to share this time at home with you. So let me start today's lecture on the unseen universe and how it impacts the world we see. And I will discuss some challenges for theory and experiments and tell a bit of how theorists are thinking about them. Okay, so everything we do as theorists is following the scientific method invented by Isaac Newton. Newton used mathematical equations to describe the invisible force of gravity and explained empirical observations. For example, the apple falls from the tree, the movement of the planets around the sun, and the moon orbiting the earth and causing the tides. So although it took until Einstein's theory of general relativity to really explain what the gravity force really is, the formation of a space due to matter, Newton's Principia, which is the way it was called here, gave a quite accurate description to explain the world we experience. So today, we use the same basic principles to ask the big questions of science, and we use math and laws of physics to understand what is behind the scenes. So let me go there. So actually, preparing this lecture made me think of watching the Flying Dutchman, Wagner's opera that you may have seen, in Berlin with my 5-year-old son long ago. It was probably a stretch to bring him there, but he was fascinated. And actually, we were sitting, let me just use the pointer, laser color green. And okay, so we go there. So in fact, as I said, we were sitting precisely here, okay? So we have a bird's eye view of the stage. So in the Berlin Opera House production I saw, the ship that you see here suddenly came out from the stage towards the public flying, very impressive. What we saw was amazing, you know, like the moon appearing every night and disappearing every day. But we didn't see was firing our imagination much more. So today we are going to go through a journey to explore the invisible world, which makes possible the magic that we see in our everyday lives and also in the whole universe. So I will start with these pieces of the invisible world. First, I will talk about an invisible field of energy. It allows all we see, stars, planets, the moon, people, and opera houses to exist. Dark matter, it shapes the fabric of the cosmos. It holds our own Milky Way together, and it distorts the images of distant galaxies. If you think about the theater analogy, what we cannot see at all, but we know it must be there. For example, the cables of the stage that hold the ship and make it appear to be flying over a tempestuous sea. The virtual particles, they exist for an instant and disappear in the next. But as we shall see through this lecture, they have long-lasting results and implications for our world. In the theory analogy, the musical chords be vibrating for an instant and just be in silence. They are also ephemeral, but profoundly touching our senses in a very lasting way. And finally, the ghostly, omnipresent neutrinos, the most elusive particles in the universe. If I think about the theater analogy, I will think about the air we breathe. So let's start with invisible Higgs energy field. Okay, so it is a field of energy that permeates all of space. The one example we know is here, okay, is the Earth magnetic field. So it has a source, the Earth, a direction determined by the Earth spinning around itself. It is invisible, but we know it is there because it pulls on the needle of a compass and makes it point to north. The invisible Higgs energy field, which I very much hope you are seeing clearly here, is produced by itself. That's already quite puzzling. And although it affects us, it does not pull us in any given direction. But we know it is there because it gives mass to particles. Our understanding, what it means here, modern physics, or what Liz referred to as our standard model of particle physics, predicts that the Higgs field turns itself on everywhere in the universe in the first moments of the Big Bang, giving mass to particles. Particles such as the one that makes you and me and the stars shining in the night. To clarify, the three elementary particles our bodies are made of are the electron and the up and down quarks. And the two last ones are the ones that make protons and neutrons that are in atoms. If you would now turn off the Higgs field again, everything would disappear from existence, and the world as we see it will fall apart. So how do we know the invisible Higgs field is real? That's a very good question to ask, correct? So this invisible field of energy was proposed by Mr. Higgs here 58 years ago. At the Nobel Prize ceremony, not so long ago, he said to me and to my good friend, the CERN Director General Fabiola, my first paper was rejected because they say it was not relevant for real physics. It has beautiful math in it, though, he added. Of course, as you can see here, these equations may not mean anything to you, okay? Just that this musical notation might be undecipherable to the uninitiated, but both can be interpreted to reveal a harmony in nature. Anyway, Mr. Higgs said the second version of his paper, he added that he could prove the existence of the invisible Higgs field by finding its associated particle, the Higgs boson, a new particle. So let's go and look for the Higgs. And as you probably all know, my friend Fabiola and her colleagues did indeed look for and discover the Higgs boson at the CERN Large Hadron Collider. It was announced on July 4th, 2012. It made a big splash around the world and brought tears to Mr. Higgs' eyes. So to make a discovery of this magnitude, it took half a century, and building the Large Hadron Collider, we call it LHC, the most complex, most expensive, and largest machine ever built by mankind. The LHC, as you see it here, is in Geneva, Switzerland. And you know, you have a really big experiment when it is big compared with an international airport. I would like to add that Fermilab Large Hadron Collider Physics Center nucleates the US efforts in one of the two big experiments. One is CMS, the other one is Atlas, the two experiments that discovered the Higgs boson, and had played the Fermilab LHC Physics Center a crucial role in the Higgs boson discovery. So now, let me just change this because I need to do that, Okay, so what I will try to show you now is an actual collision when the Higgs boson is created and transformed into matter particles that we see with our cameras. We call them specialized detectors. We are recreating conditions of the early universe when it was about 1/10 of a billionth of a second old, a real baby. So let me just start with the movie here. So we go inside the LHC in a tunnel, 300 feet underground. We have the protons moving inside the ring. They go very fast, almost at the speed of light, and they cross the French-Swiss border. They don't need passports, nor vaccination cards, or negative antigen test to do that. Here, we see the proton itself with the quarks and gluons wiggling inside. And so they accelerate. One beam of protons go in one direction, the other goes in the opposite direction. So they arrive at one of our biggest detectors, which is the Atlas detector. And when they meet, kaboom, the protons collide and they make a lot of debris. But among this debris, they also make a Higgs boson. How do we know we have made a Higgs boson? It's because it immediately transformed into particles that we can identify well in our big detectors. Here we see the Higgs boson transforming into 2 electrons, the green tracks, and 2 muons, the blue tracks. We will come to these muons a bit later. So I told you that in order to discover the Higgs boson, we need actually the big LHC. But you could ask further, what made it possible to discover the Higgs boson? And the answer for that is virtual particles. All the fundamental particles of nature that we know can behave as virtual particles as a result of the uncertainty principle, first thought of by physicist Werner Heisenberg. This is an element of quantum theory that expresses the wave-like nature of particles. So as a result, it is possible that for a very short time, there is a large uncertainty in the energy here, okay? And so this allows the particles to spring into existence from nothing. So this means really that empty space has virtual particles whose physical effects can be predicted and measured. This, at least for me, mind-blowing feature of the quantum world plays a crucial role in all the experiments that we do in particle physics. So, for example, if you look how the Higgs boson was discovered, you will see that virtual particles are at the core of it. So here we are doing what we do at LHC. We are smashing 2 protons, one against each other. And the protons are really made of quarks and gluons, that are the particles that glue the quarks among themselves. So when we smash the protons, what really collides are 2 of the particles they are made of. So you could have thought that to make a Higgs boson, we need to collide 2 heavy particles, since they are the ones that talk the most to the Higgs. In reality, the particle's mass is one-to-one related to how much they talk or they connect to the Higgs. But in fact, what we collide are 2 massless particles that are these gluons in the quantum vacuum. And the gluons take advantage of the fact that they can produce for a tiny instant virtual top quarks. The top quarks are very heavy cousins of the up quarks. In fact, they are the heaviest known particles that are fundamental. So without this trick of virtual particles, Mr. Higgs would still be waiting for his boson to be discovered. And as a bonus, I want to say that the top quark particle was first discovered at the Fermilab atom smasher called the Tevatron in 1995. Okay, so we got the Higgs boson. With that, Mr. Higgs' theory explains how particles get mass via the invisible field of energy. That's great, but still we have a lot to learn. The Large Hadron Collider will keep collecting data until 2042. Oh God, I don't know. I don't want to even think how old I will be at that time. So we will try then to understand better our new friend, the Higgs boson, and to explore what lies beyond. Our really big next challenge is now to understand what is dark matter. So we know that dark matter exists because galactic and cosmological observations show that there is much more in the universe than what we can see. However, we don't have a clue what dark matter is made of and why it is there. Okay, so there is a strong evidence of dark matter from its interactions with visible matter in our own Milky Way. In the 1970s, Oh, thought I was, okay, going again there. So in the 1970s, Vera Rubin and her colleagues started to measure how fast stars that are moving in galaxies like the Milky Way move as they orbit around the center of the galaxy, okay? So from standard gravity, we would expect that stars that are very far from the center, let's say here, okay, would be moving much slower than those that are at the level of our solar system. This is this red curve that it has been calculated, assuming that the only matter that exists is what we see as luminous matter. So there is no dark matter inferred in that calculation. But this is not what Vera Rubin found. What she found, what she measured is here, correct, is that even the most distant stars in our galaxy are moving about as fast as our sun in their orbits. And this is this line here. So the laws of gravity, as we know them, would say that those stars should just fly away. They could not be trapped by the gravity that is coming from the luminous matter we see. But the explanation is that this is the visible part that we see is just inside a much bigger part that is what we call dark matter. In fact, about 90% of the matter in the Milky Way is made of dark matter, not from stars or planets or nebula. Okay, so today we have many more sources of evidence for the existence of dark matter coming from many different observations. And let me just highlight one here that is called gravitational lensing. So as Einstein told us long ago, space-time, as we see it here, is distorted by the gravitational effect of matter. That makes the light for distant objects move in a curved line as we see it here. The effect of gravitational lensing, as we call it, is to distort the images now, because we see these two areas of light coming on. And we see it distorted by the bending of light by strong gravitational fields. And we see them in our telescopes as these distorted images. And I couldn't avoid to put this nice picture of distorted images from curved surfaces from our very own Chicago beam. Not the same source, but a nice connection. So nowadays we can use computers, very advanced computers, to make a map of where all the mass has to be in order to produce these distorted images. And as we see here, this map of the galaxies showing these pointy spikes are galaxies, but then there is a big mountain of something else, and this is what we call dark matter. So we know dark matter is there, but you could ask, what do we really know about dark matter? And unfortunately, the answer is very little. All what we have seen is that dark matter couples to us gravitational. We have not seen any other type of interaction of dark matter with us. We know that this is the most abundant form of matter, altogether makes about 85% of all the matter in the universe, 85%, and we have no clue what it is made of. It needs to be something different from all the particles we know, okay? It can be particles we have never seen. It can be some very heavy compact objects. It can be something that likes to behave more like a wave, than like a particle, or it can be a combination of many things. We don't know. Also, it may be part of a larger, invisible dark world with new dark forces. And in fact, this dark world may not be talking to us besides through some portals. And one of those portals could be our own Higgs boson. So what we would like is to detect the dark matter in the laboratory. Indeed, we know it is out there, and we would like to find ways to catch it in our detectors. Even better would be to try to make it at a particle accelerator, the LHC, as we did to create it, as we did with the Higgs boson. Okay, it's hard to design an experiment to look for something that you don't know what it is. So you don't know what you're looking for. So the strategy we have is for theorists to make educated guesses of what the dark matter can be, and for experimentalists to find novel ways, many novel ways to detect it. Both theorists and experimentalists work close together to find the solution to this big mystery. Here are some people at Fermilab, and not all of them, some theorists at Fermilab, who spend a big part of their time thinking about what it is dark matter. Mike Turner here, who used to be a distinguished fellow at Fermilab and is professor at the University of Chicago, was the one who thought about the name or coined the name WIMPs, weakly interacting massive particles. And this is one of the most promising ideas for dark matter. So as theorists, we try to connect the existence of dark matter to some other mysteries of particle physics. We want to try to put all the pieces of the puzzle together. This, of course, leads to lots of interesting guesses with very funny sounding names like quark nuggets and axions of all types. And of course, the WIMPs that are somewhere here. And we imagine different extensions of the world we know where there could be additional dimensions of space. There could be enhanced harmonies of nature. It's one of them, we call it supersymmetry. And in most cases, there are new forces that we have not experienced yet. So, meanwhile, of course, experimentalists are pursuing three basic approaches to find dark matter. And let me just very briefly comment on them. So the first one is to look for evidence out in our galaxy of dark matter that was left there and is now colliding with ordinary matter or decaying into it. And so what we see, for example, is the Ames detector in the International Space Station. We're trying to measure or to see gamma rays or neutrinos or charged cosmic rays, like, for example, positrons. And we are trying to see if there is something more than we would have expected from our standard model understanding, from the particles we know. The second is to try to produce dark matter, as I mentioned, directly at the LHC, to create dark matter at the Large Hadron Collider. That would be amazing. So why? It's because it's very controlled. It's a very controlled situation. We know how much energy we put in a collision. And if, when we look at the particles that we put the energy with some proton collisions, and we look at the particles that were produced, and we can measure their energy, and we see that some of this energy is missing, then we think that this energy could be going into dark matter particles that fly away from the collision. Finally, a very very powerful way of looking for dark matter is to build many different types of ultrasensitive detectors, which might catch dark matter particles in the laboratory as they stream out of space, which means they hit somehow our detectors and we can get some type of signal. In all areas there is leadership at Fermilab in collaboration with the University of Chicago. And right now, there are novel possibilities with quantum technologies that will allow us to search for dark matter particles in a very wide range of possibilities, and those that have been up to now the most elusive. So dark matter exists, and we are leaving no stone turned around. I hope I convince you of that. So now let's move on and look closer to virtual particles and what they may bring along. They may also be connected to dark matter. We don't know. So let me go back here. Okay. So now, last April, I was thrilled to watch my Fermilab colleague, Chris Polly, unveil the result of the Muon G-2 experiment for an audience of thousands of people. And maybe some of you were there watching. I hope so. An experiment, this Muon G-2 experiment is an experiment that is designed to be sensitive to the effects of virtual particles. So I have to say, suddenly, I was remembering a time many, many years ago when I was traveling in a high-speed train, like the one you're seeing there, away from CERN, next to my next job in Germany, looking through the window at the flashing scenes going by. Each was just a few flickering frames. I saw houses and people and nature, all gone in the blink of an eye, but enough for my imagination to feel a full story. At that time, I had just finished analyzing the flickering effects of virtual particles on a special property of the muons, the same type of property that is being now under scrutiny at the Fermilab experiment. Today, again, I am trying to discover the story that is behind the muon G-2. So going back here, okay, whoops. So, you may first ask yourself, what are these muons? Well, and how do we experiment with them, okay? So muons have the same physical properties of the electrons, and that's why we call them cousins of the electrons, but they're heavier, about 200 times heavier, and they're unstable. If they are at rest, they will just live 2 millionths of a second, 2 microseconds, as I would like to say. So we see here showers of high energy particles that occur when all these particles occur when very energetic cosmic rays strike the top of the Earth's atmosphere. So here is a cartoon of what happens here, okay? And in this cartoon, we see that when a cosmic ray strikes the upper level of the Earth's atmosphere, it will create many particles, and these particles in turn will create other particles, and among those particles that we create muons. Muons and what we call anti-muons, okay? So in this picture, it's funny, they put a Concorde airplane, which flies up to 60,000 feet, and a helium balloon that flies twice as high. And I guess this is just to give you some perspective. So muons can hit us and the Earth. And in fact, there are 10,000 muons are passing through our body every minute, right now, for you and for me. Okay, so before taking before going more into what we do, what muons can tell, let's get a closer look at how the Fermilab Muon G-2 experiment works and how the muons are produced under controlled conditions. So what we have is accelerators, which smash high-speed protons at a target, mainly nickel target in this case, that finally produce muons. Then the G-2 experiment here puts these muons inside this magnetized loop where they circle around and around in a vacuum until they decay. Okay, so you may pause for a second and said, great, so where did you take this 50-foot long ring of magnets from? And that's an interesting question. About 10 years ago, we got it for free from the Brookhaven National Lab in New York, where it was used there to run 20 years ago, another Muon G-2 experiment, which produced amazing results that, however, were still not conclusive. So the 50-ton apparatus that you see here was shipped from Long Island to Chicago through an ocean and rivers and highways, and was really a tour de force, and it arrived to Fermilab in a quite stormy day. So what the Fermilab experiment measures really is the wobbling of the muons. So muons have electric charge and a property that is called spin. That the spin reacts to magnets. So the spin points in a direction like the needle of a compass. Here, the spin is these yellow arrows. So here is a diagram, okay, that shows First of all, starting from the protons into the target, producing the pions, then at the end producing the muons that are injected into the ring, okay? As I said, the magnetic field is there and makes the electrically charged muons to orbit around the ring at very high speed, almost the speed of light. But it also causes the spin, if you see here, so to precess, okay, like a gyroscope, when the muons go around the ring. And if that would be the case, you will see always these yellow arrows together with the pink arrows. But there is also a small wobbling that you see it here, okay, of the muon. And this wobbling is proportional to the factor that we call G minus 2, hence the name of the experiment. If you want to read more about it, I strongly recommend that you read the cover page article of Scientific American that was on the month of October. It is an excellent article. I wrote it. So what causes the wobbling? The vacuum factor. If muons were alone, just on their own, with no company, in the vacuum of the ring, their spin will not wobble and G would be equal to 2. So G minus 2 will be equal to 0. And this is what we see here, muons alone. However, empty space is never really empty, as we discussed before. Virtual particles appear and disappear in the experiment, and they interact, they talk to the muons. And when they talk to the muons, they change the behavior of the spin precession of the muon. And this is why G is larger than 2. So this actually would be the effect that will already be there if we have all the particles we know in the standard model. So nothing new needs to be there. So in reality, for example, this is one example where the muon really talks to a virtual photon that springs into existence for a second and then disappears, and a virtual muon that changes its mass and then goes its own way. Okay, so we theorists, or some of us, can compute, the stronger ones, can compute the muon wobbling expected from all the known particles in the universe. We do this calculation very accurately, and then we can compare the wobble we measure in the experiment with the wobble that we will predict, just assuming all the interaction of the muons with virtual particles that are only the virtual particles of the particles we know exist. Okay, so what happened is that, going back to April 7, 2021, okay, when Chris Pauly presented the first results, the point was that the wobble the experiment measured was bigger than the one we predicted, assuming that only the particles we know, were present there to interact with the muon. Okay, so as the New York Times put it, the particle's tiny wobble could upend the known laws of physics. So this was a big surprise and caught a lot of attention from the whole world. In fact, Mike Bloomberg said the most extraordinary event of the year. And I would say that even Luke Skywalker said that the force seems to be with us. Okay, so the Fermilab experiment measured significantly more wobbling than predicted from all the virtual particles that we know exist. The discrepancy is so big that we are close, very close, to the very rigorous threshold we require to claim discovery, as we did with the Higgs boson. The results seem to challenge our understanding of modern physics. What this means is that more particles than those that our standard model of particle physics predicts, and we have seen, seem to be around us. Some other particles we don't know seems to be hopping around. So what could explain the results of the Fermilab experiment? Well, it has to be something new, as I said. We know that there must be things that are new already because we don't know how to explain their matter. And also, because the properties of the Higgs boson that we have measured are still quite mysterious to us. So theorists, as you see here, a bunch of them, just really a handful compared to how many are thinking about that, are proposing many scenarios with new particles and new forces that are very strongly constrained by the data that is coming from many, many experiments looking in many corners of space. And in fact, some scenarios are exciting because could connect this muon G-2 special behavior with dark matter, or even explain puzzles that we have seen at other experiments where muons seem to be behaving weird as well, like at HCB at CERN. So muons may be telling us something with implications far beyond themselves. We see here Sheldon quite excited. But where are we standing now? We have already collected about 10 times more data than what we have analyzed, and this will be analyzed in the next 2 years. And meanwhile, theories are really rechecking the theory predictions. We have been refining these predictions for the last 20 years. So don't think that was a back of the envelope calculation in any way. But some of the details are really quite hard to compute. And although all theories agree on the results, we're still trying to look at it once again. Okay, so now we move to our last topic of the evening, that is neutrinos. As I show you in our cosmic ray cartoon, I show you that the muons were made in the case of other composite particles like pions, but when they appear, they always appear with neutrinos. In that case, muon-type neutrinos. They don't appear alone. So neutrinos come from many, many, many sources. The sun shines almost as brightly in neutrinos as it does in light, 65 billion neutrinos per centimeter square of Earth surface facing the sun. Wow, and this is a beautiful picture of neutrinos from the sun. Atmospheric neutrino, as I told you, you produce a muon, you produce it with a neutrino. You produce a muon, you produce it with a neutrino. In this case, it's an antineutrino. In this case, it's a neutrino. Supernovae, okay. When a massive star arrives to the end of the life and it collapses, that's a supernova event, it radiates almost all of its energy in the form of neutrinos. In fact, as I show here, 99% of the energy of the supernova explosion is carried off by neutrinos. These neutrinos come in all flavors and are emitted of a time scale of several tenths of a second. Then there are the relic neutrinos. These neutrinos are really old. They come from a second after the Big Bang. This is the time when the neutrinos cease to interact with all other types of matter. But since neutrinos don't talk to anyone after that much, they are still around there and we can look at them. Then there are, of course, geoneutrinos. There are a lot of neutrinos that are produced from the decay of radioactive elements in the center of the Earth. And many other radioactive elements, like potassium and banana could produce neutrinos. So finally, in this slide, there's two other ways that we can actually make neutrinos ourselves. One is nuclear reactors. So this is in a process that is called beta decay. And this means when a neutron goes actually to a proton and an electron and an antineutrino. And so we can produce them, these neutrinos, and these neutrinos are carried away, but they don't carry any radiation themselves, but comes from radioactive decays at nuclear reactors. Finally, at Fermilab, we use our very powerful particle accelerators to produce extremely powerful neutrino beams in very controlled conditions. And this is very similar to the way we produce the muons. As you see here, we have the protons, a target, a focus area with pions and kaons, for example, depending on the intensity of this proton beam, we could get different type of complex particles here. And then these particles decay into muons and neutrinos. In this particular case, for the muon, for the neutrino beam, we stop the muons with this concrete wall there. So we are analyzing data from many experiments to collect more information, and we are also launching new experiments. All that at Fermilab to study neutrinos and their mysteries in a very dedicated way. So in fact, if you look at this Fermilab campus today, if we wouldn't be in pandemic, we will all be sitting in the beautiful hall here at the high rise. But unfortunately, I'm talking to you on Zoom and I cannot see you. But okay, so very close to the high rise at Fermilab, there is this complex with many, many neutrino detectors. So the beam is somewhere here, goes around here, and enters here, the neutrino beam. Here it says. So different type of detectors. Some of them have taken data already, like Muon, and they are analyzing still their data, and they have produced interesting results. Some of them, they are ongoing, this NOVA experiment. And actually interesting is this NOVA experiment is one that is in Fermilab, and we call it there on-site or short baseline because it's close to the beam, to the source. But there's also another NOVA detector that is in northern Minnesota, 500 miles away from us. And this is to study better how the properties of neutrino change when they travel. And now there are the new detectors coming, is Icarus here and SVND, all of them to study the best we can the neutrino mysteries. But let me just do one little step back and tell you a little bit about neutrinos before moving forward to our next project at Fermilab. And so neutrinos really were first proposed by Wolfgang and Pauli in 1930 to explain radioactive decays. For example, as I said, a neutron transformed into a proton plus electron plus a neutrino that happens to be its antiparticle and now antineutrino because of some conservation of properties. In fact, you may ask where the name neutrino comes, and the name neutrino was coined by Enrico Fermi, the reason we are the Fermi National Laboratory. And what it really means is from the Italian, little neutral one. So neutrino is the little neutral one. So neutrinos, as far as we know, come in three types of flavors: the ones that come with electrons, their cousins, the muons, and there are even heavier cousins, the taus. So electron, muons, and tau neutrinos. Again, the tau neutrino was actually discovered at Fermilab in the year 2000, not so long ago. So about 1 trillion of neutrinos pass through your hand each second. That's amazing. Neutrinos have tiny masses, but not zero. Originally, we thought that they could have zero mass, but now we learn that they don't. And the reason they don't have zero mass is because they undergo a strange phenomenon that is called neutrino oscillation. And what it means is that as they are traveling, one electron neutrino or a part of it changes into a muon neutrino or back or into a tau neutrino. So they can change from one flavor to another as they travel. So Fermilab experiments are searching actually for a fourth type of neutrino, what we call a sterile neutrino. There could be even more types of sterile neutrinos, but at least one. And this neutrino only talks to us through oscillations, so through mixing, through interactions with the standard neutrino types that we have seen. Okay, they also talk gravitational, but because they are usually so light, the interaction would be small. So if sterile neutrinos exist, and this is one of the biggest things we're trying to understand, it could provide solutions to several mysteries in physics. And among them are, they could explain some peculiar behavior. I said that like mini Muon, one of the experiments at Fermilab and other experiments otherwise, and other places, they have seen things that are not matching perfectly what we expect. And so maybe stellar neutrinos, there's a signature of stellar neutrinos. Stellar neutrinos could be actually the dark matter. They are kind of very relevant in trying to explain. I told you that all the masses of particles are explained through the interaction with the Higgs field, but these stellar neutrinos can give us a variation of the mechanism of mass generation for the neutrinos. And excitingly, they can also tell us something about why there is matter in the universe. So the next big science experiment at Fermilab, you may guess, is trying to answer those questions, is what is called the Deep Underground Neutrino Experiment. It is under construction. Will start running by the end of this decade, and will keep running for a couple of decades to come, at least. And it's an international experiment with more than 30 countries participating, so similar to the LHC. So Muon will be for neutrinos, like the LHC is for the Higgs boson. And so Muon will be, so we will produce these very powerful neutrinos with a new accelerator complex called PEP2 here at Fermilab. There will be one Muon detector here, and then we will see the neutrino beam, and then we will shoot this neutrino beam 800 miles up to the Sanford Underground Research Facility, 1 mile underground, to a huge particle detectors, huge particle detectors that are going to be there. And as you see here, neutrinos go through the Earth. They don't need any tunnel. I remind you that we have all these neutrinos going through our hand. So we don't need tunnels to send neutrinos. That's important. So with Muon, we will be able to investigate with unprecedented accuracy if the behavior of neutrinos and antineutrinos differ when they change into different types. And this is very important because if that happens, the neutrinos could be the reason that the universe is made of matter rather than nothing. Also, I told you that supernovae, when occurs, liberates an enormous amount of neutrinos. So observing neutrinos from exploding stars, if we are lucky, from these supernova events, would be very important, because it may be that as part of these supernova events, there is the formation of neutron stars or even black holes. And by looking at the neutrinos in that behavior in real time, we could learn about these amazing options. And last but not least, because the detectors here will be actually 4 detectors with 17,000 tons of liquid argon each, so humongous, we are thinking that maybe we can finally see proton decay. We have not seen proton decay. The proton is very long-lived, but if we think about unification of forces, most ideas of unification of forces will predict this proton decay. Okay, so wrapping up, theorists are trying to decipher the pieces of the puzzle one by one. At Fermilab, we explore the behavior of muons and neutrinos with unprecedented detail, as I tried to convey to you. We search for their matter and their forces with new technologies. And we are a big part of the LHC, where we try to directly produce and discover other Higgses, dark matter, new forces, and even stellar neutrinos. So the job of theorists is to pull together all the pieces from what we see or what we do not see, that also gives information, in experiments around the world, and get an idea of the big picture of the universe. So we are using Isaac Newton's scientific method, coming to the beginning, but instead of waiting for the apples to fall, what we are doing is we are shaking as many different kinds of trees as possible and see what it comes. So the theory's job is to suggest which trees to shake. And we are guided by math and the laws of physics and experimental data. And we hope to find out which type of marmalade our universe is made of. Thank you.